Good morning, everyone. I'm so glad to be here to share with you my perspective on the small-scale piezoelectric energy harvesting. We have been working on this area for about 15 years. And in the tutorial today, I'm going to talk about more material and mechanical perspective of the small-scale piezoelectric energy harvesting transducers. Okay, so this is the outline of my tutorial today. First of all, I'm going to talk about the introduction and motivation of this research. And then I'm going to talk about transducer, that's more about mechanical perspective, including electromechanical modeling is generally quite complicated, and also about model simplification and design trade-off. For an engineer to design a bigger picture, we need to have more simplification and to understand the underneath still is small, so we can try to get a trade-off or balance between like material, mechanical perspective, also like the fabrication difficulty, something to finish the design goal. I'm also going to talk something more, for example, like bin-shape optimization, and also alternative excitation instead of conventional basic excitation. It's actually in the past year a project I'm working with Miguel on the rotational excitation. They generally seen in like machines in factories. And the last part of the tutorial will be about material perspective. And for material in small-scale transducer, we have two major material. One is substrate, the other is piezoelectric material. So I'm going to talk about the substrate material selection, the piezoelectric material selection, and also because it's small scale, so we are talking about piezoelectric films. And the films here, I will to talk about thin and thin films. In general, about 2 micron. If the thin thickness is under 2 micron, I will say it's thin film. If it's thinner than 2 micron, for example, like our state-of-the-art transducer fabricated from my lab, we have the thin thickness around 10 micron, and it's a so-called thin film in this tutorial. And I will talk about different deposition process and different consideration you have to take into account for your final design. Okay, so motivation, everyone is talking about Internet of Things, and it's predicted by Cisco some years ago. Say by 2020, there will be 50 billion devices be connected with so-called IoT devices or smart devices. And 2020 is not far away from now. We are now in 2019, so next year we can judge if this will be realized or not. But actually, a lot of people are saying we are actually ahead of this prediction. From now, probably it's already more, including all the computer or the servers that serve before internet. And I heard the other numbers say about 2 years ago, the machines on the internet are actually already more than people connected on internet. You can imagine when you like Google something, you can get a response in very tiny time. So there are actually millions of servers that's hiding in the data center of Google to serve all this kind of internet service. So the Internet of Things concept is we are going to have more and more smart devices with different kind of sensors. So that will be served as like part of the smart city, smart building, smart home, or smart factory. In the industrial area, people are talking about Industrial 4.0. That's actually something very similar. So talk about prediction, it's more real if we talk about real application. This panel you can see here, it's actually a smart home control panel. That's my hobby project in past 2 years. In my home, I already have almost all lines that's control automatically with Wi-Fi light switches or maybe the light switches. And also I got several ZB sensors like human motion sensors, like door sensors, and so on. And also, of course, the temperature and humidity. So here you can see is the outside temperature, outside humidity, and the green and the red trace is the temperature in my living room or bedroom for 24 hours. Okay, so all the sensors or light switch behind my setup in my home mostly are transmitting the control signal wirelessly. For example, like this two is a human motion sensor. It's about some size. It's not very big. And this is the door sensor. It can get the sensing signal when you open or close the door. And it's based on ZB protocols, so it's actually quite power efficient. And you can see here, it's a battery here, over here. And the prediction of the battery lifetime is about 2 to 3 years. And already finished this setup for like more than half a year, so you can see the battery still over 100% till now. I'm not sure if this is true or not, but if it is true, this should be most of the time good enough. But still, you need to remember, in order to avoid to get my wife mad, I have to hide all these sensors behind some difficult, some points that's difficult to reach, to hide them. And I can now, I'm now starting to worry about, even it's 2 or 3 years later, there are about 30 this kind of sensors in my home. So if I had to replace all the battery one by one, that would be a big job. And for the other applications, for example, smart city, in the city I'm living now, in Taipei City, we are talking about a lot of smart city projects. For example, we are going to have a smart parking system, like tree-side parking, roadside parking. The Taipei City government is planning to put a parking sensor underneath the car as buried on the ground of parking space. So if it's powered by battery, and 2 or 3 years later it's running out of battery, and you have to dig it down and replace the sensor and bury it again, it will be a huge job, and the maintenance cost will be huge. And also, when we're talking about smart factories, if there are like 2,000, 3,000 different kind of sensors all around the smart factory, to replace all the batteries will be a big job. So for the dream of any harvesting people, we are talking about one day we can replace all these kind of batteries, so we can harvest energy from the environment, including like light, vibration, different kind of ambient energy sources. And this is about power generation and consumption. The concept the set power system, I mean, to power certain kind of devices autonomously without battery, is actually not a new idea. For example, like a Seiko watch, 20 years ago, they had like a kinetic design with like imbalance rotor. When you are working, it can wind the rotor and to generate electric power. Or even go back further, the mechanical watch that's hundreds of years ago, that's also set power, was using also impedance rotor that's winding how to say that, winding a spring, a circular spring to store power. So it's not new, but for this kind of like watch or smart calculator, you can also see it's powered by small solar panel. It's actually in the power range here, about nanowatt to microwatts. But in order to power the sensors and also the wireless transceiver, it actually consumes more power. So for the nowadays energy harvester, we are talking about the power range from like microwatt to milliwatt range. for a typical IoT nodes, like the smart home sensor I just presented to you. When it's in idle, the power consumption should be lower than 1 microwatt. But when the transceiver is turned on, sensor is turned on, at the peak power will be about tens of microwatt. It depends on the range you want to reach for the wireless communication. Okay, so here, this range, about 10 microwatt to tens of milliwatt, is a small-scale energy harvesting we can reach. And it's also, in this area, typical IoT devices, smart devices, we can already do something to power the sensors and also the wireless transceivers. Okay, so this is a literature review. In this area, we are talking about the chip area smaller than 1 centimeter square. That's fabricated with MEMS technology, micro machine technology. The whole research is started about 2005. The first paper is from MIT, and we see a paper from Shanghai Jiaotong University, and also like Auburn University. And this is the first paper we published in 2009. And from 2005 to 2009, you can see the chip area is actually much smaller. It's about millimeter size, and the power it can generate is quite small. It's a single-digit microwatt, about 1 to 3 microwatt a lifetime. So, like what I said, in this range, it's already enough to power the IoT devices in idle mode, but it's still not enough to power as in when it's transmitting or turn on the sensor to do some kind of sensing. Of course, we can have certain kind of energy storage buffer, like a capacitor or battery, to set power when it's generating power. We set it into the buffer, and like for example, 1 or 2 hours, we turn on the sensor or the wireless transceiver. We call it a duty cycle control. It's a typical thing in nowadays wireless communication, including our cell phones, to do power saving. But in general, we will say to do a meaningful application, at least 10 microwatt is actually quite important. If the overall power generated is more than 10 microwatt, I still have to consider about like the losses on the interfacing circuit and power conversion, power converters, and that will be very difficult for real applications. So, starting from 2009 to 2019, the past decades, we see researchers all over the world. We are working very hard. So, first of all, you can see the order of magnitude improvement here. The unit is still microwatt, so it is cut here. And the state of the art today, 2019, we can already see the transducer smaller than 1 centimeter square that can generate output power more than 100 microwatt. For example, like this one, that's fabricated from my lab. We can already generate about 3 microwatt on 0.5G. 0.5G is actually a very small vibration. It's about, for typical fans, like circulation fans, for in a building, the vibration is around 0.2 to 0.4G. So 0.5G is a little bit more. If you touch the vibration of 0.5G, you can almost feel, you cannot actually feel it's moving. It's a very little vibration amplitude. So here you can see like this is iMac from Holland, Michigan University, Kyoto University, and my university, and also Shanghai Jiaotong University. There are a lot of papers that's published in this area, and we can see huge improvement. Okay, so this is the demo video. That's we created about 3 years ago, and I should pause the video to say something first. Okay, so inside this package, this is actually a micro-cantilever that's fabricated by my lab with a piezoelectric thin film that's fabricated on a stainless substrate. And on top is a PC board with a power converter on the top side and a Bluetooth low energy with temper sensor on the bottom side. And here you can see all the power this module comes from the 2 wires from this energy harvester without any batteries or with any wire connection. And here we already, we still need to have energy buffer over here. This is the 2 very big caps. And with this setup, we can transmit the temperature readings from the Bluetooth sensors to a smartphone. And in the video, you can see it can transmit around 2 to 3 seconds per readings. That's completely powered by the vibration energy harvester. And this is a small shaker that's simulate about 0.3 to 0.4 G. That's the vibration level. I just say you can generally see on the circulation fan. Okay, you see it's okay? You can see your reading changing. Okay, so from this video, I want to tell you for this kind of self-power design to replace battery, it's not that far from us, but of course it still has a lot of limitation. For example, the vibration frequencies and the vibration levels, or like in factories we are talking about maybe rotary excitations, and we have to design the transducer to match different applications. For now, the major difficulty is we cannot design a sensor that's fitting all possible applications. And this is also why here I'm talking about the mechanical and material perspective. How do we design a transducer based on the application needs? Okay, so this is actually Thursday. I'm talking more about the system in a package concept. This is actually a project ongoing. The project is actually just started, and we already have quite good piezoelectric energy harvester. We are also now fabricating the sensors, and also we are now working on integrated circuit, the power converters. And of course, we still need to have certain kind of passive components. And in 3 years, our target, our goal is to integrate everything together into a package, like an IC. So actually 2 years ago when I was in Power MEMS, I saw in the exhibition Aero Devices as IC company. They have a very good training, and they say in the future this kind of IC will be a 0-pin IC. What's 0-pin IC? It does not need to have a pin to interconnect with other IC circuit board, because it can generate power, it has sensor, and has circuit wireless communication capabilities, so it does not need to have any pin. It can sell power to sensing the signal it requires and transmit wirelessly to the data collection point or to the clouds. Okay, so I'm talking about this, all of the 3 parts more on the Thursday talk. And today I'm going to cover the piezoelectric energy harvester more. Okay, so for the transducer design, first of all, you're probably already familiar with the piezoelectric modes. And for a piezoelectric material, when you have a force, because we are doing energy harvesting, so we have to have certain kind of external forces. And when we have forces to have deformation of the piezoelectric material, when we have electron and with a closed loop circuit, we can generate current that's because of the external applied force. And for the electric fields and the force fields, we have 2 choices. The first one is like this one, external force field, applied force, and the electric fields is perpendicular, and we call it a D31 mode. one in 3 direction, one in 1 direction. And the other choice is if we have the electric field that's in parallel with the force field, we call it as will be a 3-3 mode. So with D31 mode and D33 mode, we actually have different piezoelectric constant, D31 and D33. And for typical PCT, ceramic piezoelectric material, D33 is about 1.5 to 2 times larger than D31 modes. So a lot of people are talking about D33 transducer could be a better choice because of larger piezoelectric constant. So for a simple cantilever structure, if we want to harvest energy in 3-1 modes, it's like cantilever beam, you have a proof mass, and when you have the best excitation, the proof mass will move. You will bend the beam, and so because of the bending of the beam, the force relation or the stress fields will be in a beam axis. And if we have a bottom electrode and top electrode, the electric field will be perpendicular to the stress-strain fields. So this is the 3-1 mode we just mentioned. But if we want to harvest the 3-3 mode, then we need to have so-called interdigit electrode. So the electric field will be also in this direction. That will be in parallel to the beam axis. So we can harvest with 3-3 mode. And like I just mentioned, the D33 piezoelectric constant is in general larger than 3-1 modes. In order to model this kind of 3-1 mode and 3-3 mode, we can do like a unicell separation of the cantilever beam. And this is a 3-1 cell, this is a 3-3 cell. And with certain kind of mechanics and piezoelectric modeling. I'm not going to talk about the detail. This side is actually the mechanical. When it's in resonance, we can see like an inductor, a resistor, and capacitor. And this is ROC. It's actually from the mechanical side. So it's like spring proof mass and spring constant proof mass and damping. And with the transformer, on the other side, this is actually the electrical side. We have a steady capacitance for the piezoelectric material. And with the oil ballooning beam theory, in the end, we can get a very complicated equation here. This is the voltage output, this is the power output, and it's actually with a lot of parameters, including the piezoelectric constant, like the Young's module, mechanical parameters, and also geometry parameters, for example, the thickness, the length, and the width of the beam. Okay, so this is a drawing my student funds. From this kind of complete complicated modeling, when the equation is kind of complicated, it actually it's very difficult for you to see the physics underneath. So we have to do certain kind of simplification and to retrieve the important parameter we want to see. For example, when you want to compare the 3-1 mode and 3-3 mode, like what we really concern is the power output and the voltage output. So here we have P31 and P33. You can see the equation is still quite complicated. And it's including the material parameter, geometry parameters, and piezoelectric parameters. But what we concern is actually the normalization here. For example, P33 versus P31, the ratio is depend on which kind of parameters. So after certain kind of simplification, we can get a very simple relationship here. For P33, the power generated from 3-3 mode over power generated from 3-1 modes. From the blue rectangle is actually depend on the material, so we call it a material filter. And on the green rectangle is mostly geometry. So we call it a geometry factor. So in material, we have EP3 and EP1. This is a Young's modulus. is renewable. And later on we are talking about, it's not only Young's modules. In general, we talk about the stiffness of the beam. So in general, EI, that's including the Young's modules and moment of inertia to determine the stiffness of the beam. And here we have the D33 and D31, the ratio of the piezoelectric constant. And like I just mentioned, the D33 is in general higher than D31. And also we have epsilon 31 versus epsilon 33. This is the dielectric constant. If this is a homogeneous dielectric material, then we will say epsilon 31 is equal to epsilon 33, and then we can eliminate this parameter. And for geometry factors, the most important factor we have here is the G and TP. And G and TP, when we go back to the drawing here, TP is actually the thickness of the piezoelectric film, and G is actually the gap between the interdigit electrode of 3-3 mode. So in the end, we can say the power generated from the 3-1 or 3-3 microcannular beam is actually inversely proportional to the Young's modulus and proportional to the piezoelectric constant, inversely proportional to the dielectric constant. And also in the geometry factor, for 3-3-1 modes is proportional to the gap between interdigit electrode, and for 3-1 mode is proportional to the TP, the thickness of the piezoelectric layer. And also from this formula for the geometry factor, we also can have the other simplification. For this term is actually depend on the total effective volume of piezoelectric layer, plus is the total effective volume. For example, here this is the 3-3 modes. 3-3 modes. We should go back to here. I'm sorry. I mean, for effective volume, if we can have a thinner piezoelectric film, thinner substrate, that means that we have a larger effective piezoelectric material, and of course the output will be larger. And for switching modes, effective volume, we have two different meanings. I will mention this later. And the first important parameter here is to have a very big gap between the interdigit electrode. But it will be very difficult to pull the piezoelectric material on the pulling process before we can activate the piezoelectric effect. So switching mode is in general not so easy. And the most important reason for the difficulty of switching mode is also here. Ideal 3-3 mode transducer, we actually want to have electrode that's buried inside the piezoelectric layer, like this, like a vertical wall. So we can get the electric field alternating in the duration in parallel to the beam axis. But in effect, for fabrication difficulty, we generally only put the top electrode on the top. Of course, there are also some research put some electrode on the bottom. So the electric field we can pick up is only like a spin effect in a very thin portion of the piezoelectric material. This means that even we have a thinner piezoelectric film, it's not helping, because the electrode on the top, we can pick up the electric field in a lower portion of the piezoelectric material. This means that for 3-3 modes, although the piezoelectric constant is higher, but in general the effective piezoelectric volume is smaller than the 3-1 mode. Even we can have a very thin film. The effective volume of 3-3 modes is not as like a 3-1 mode. Is contribute to all the energy conversion. Okay. So this is some study in 2009 and 2013. This is from my lab, and this is from Taiwan University. So you can see in our results. 3-3 mode, this is like a fair comparison. It's actually a little bit worse than 3-1 mode. And for the study from Taiwan University, the 3-3 mode is a little bit better than 3-1 mode. So it's actually not follow the prediction for, if we look at the piezoelectric constant alone, the 3-3 constant is about 1.5 to 2 times larger than 3-1 piezoelectric constant. But if you fabricate a whole transducer, there are actually a lot of different perspectives you have to look at. Then it's not that easy. The total generated power is actually not higher compared to 3-1. Okay, so if we want to do further simplification to see more theories, we can have even more simple model. Forget about the overballoon beam. Here we have a very simple model. This is a basic citation. So it's equivalent to, we have an external force to move this proof mass. So with a cantilever beam, the work done by the proof mass will be like here. You have the mass of the proof mass times the acceleration and times the tip displacement times 2, because per cycle you have force and back 2 times of the work done. And when we times the work done with the frequency, you actually get the mechanical power. So we call it a mechanical power input P in. And here, of course, very simple cantilever formula. We can now we can retrieve as the delta L. The tip displacement is actually proportional to the external force, and the L to a 3, and also inverse proportional to EI. EI is the beam stiffness. Okay, and when we talk about the piezoelectric material, when we have a certain kind of mechanical power input, we want to convert the mechanical input into electrical power with piezoelectric material. So when we talk about the performance of the piezoelectric film, like when we saw the important material, piezoelectric material parameters, is actually the D constant or E constant. But here we also have dielectric constant. So in material area, people usually use the figure of Marie of piezoelectric material in energy harvesting or sensor. Is actually proportional to D squared over epsilon. So this is the material figure of Marie. If we can have a material with higher figure of Marie, that means that the material performance is better to convert from mechanical power to electrical power. And then, for the final power output, I mean electrical power output, will be proportional to mechanical power input times figure of Marie of the piezoelectric material times effective volume of the piezoelectric material. Okay, so this will be a very simple formula so we can understand the overall physics. Here we have, if you want to get a higher electrical power output, either we can have a larger mechanical input, mechanical power input. This means there's a larger applied force or a larger acceleration, larger vibration, or we can also have a larger proof mass. But don't forget, the proof mass also that's one important parameter of the resonant frequency. And the resonant frequency of the transducer to match with the vibration source frequency. And also we can have a higher performance piezoelectric material FON. Also, like I just mentioned, you can try 3-3 modes because of higher dielectric constant. But in general, it's not easy. You have to also consider about the electrofabrication. And also the volume, the effective volume. As I just mentioned, for 3-1 mode, it's quite intuitive. You can have like single beam, single piezoelectric film, and thinner substrate. For 3 mode, of course, you can also have the same sinker beam, but you still have to remember what I just mentioned. If you only have a top electrode, then you cannot retrieve the electric field in lower positions, so it's not real effective. And okay, so we have like a design trade-off here. This is a mechanical input power and figure array of the material, and we also have the piezoelectric effective volume. So here, from mechanical perspective, we are actually have this design trade-off for these 2 parameters. So here, if we want to maximize the mechanical power output, we can have a larger proof mass. But let's also induce a lower resonance frequency, and your resonance frequency has to match to the vibration source frequency. We can also have a larger tip displacement. That means that we have to lower the bending stiffness of the beam. That means that overall a thinner beam. But again, that's also change the resonance frequency, so you have to do optimization. And also, you will have a smaller piezoelectric effective volume that will change over here. Okay, and we can also maximize the piezoelectric material effective volume. So we want to have a sinker piezoelectric film, but remember it's only working on 3-1 mode. In 3-3 mode with top electrode, it's not actually effective. So we want to have a single piezoelectric film, single substrate. This also induce higher stiffness. Higher stiffness means that we reduce the tip displacement. Okay, and also for piezoelectric film thickness, it's actually somehow limited by different material parts that we are going to talk about later. And also the other factor you have to consider is the poor mechanical strength. That means that the beam may break. So when you read a paper, you also can try to imagine something the author they do not want to let you know. For example, like I just mentioned, the paper we presented 2009. That's our very first micro energy harvest paper. We get a very good power curve, okay, like this one. What we didn't tell you is all the transducers in this paper, it can only survive one test when we test the vibration acceleration from like a 0.1 G to 1.5 G, and then it breaks. Okay, so if you are the PhD student at that time, like my PhD student at that time, he spent 3.5 years to successfully fabricate the one beam. You can get some electrical signal, and then another 1.5 years to reach the state of art at that time. And then he came to me, say, I have to graduate. It's already 5 years. So I cannot say no, you know. Well, so we published 2 papers. I had to let him go. But for scientific research, this is good enough, right? But to solve a real engineering problem, this is not good enough. We want to have a device that's very reliable. So we have to consider the mechanical strength, and also we have to consider like a fatigue issue. I'm always asked about the fatigue issue time by time. Okay, so after him, of course, I got the other PhD student, spent the other 5 years and working on a more reliable small-scale energy harvest. That's what I'm going to talk about later on. Okay, so from the mechanical perspective, the other optimization you can do is, for example, the tailored beam shape. The tailored beam shape, you can do actually 2 important things. One is to have a more uniform strength distribution. This means, for example, you can see it's light blue to deep blue. It's almost all deep blue. So it means that the strength field is more uniform, and the reliability could be better. And the other factor with this kind of pellet beam shape, you actually have lower beam stiffness. That means that at certain acceleration, the same external excitation level, the tip displacement of this kind of microcantilever will be larger than this one. It's not means it's data, but you have to design or optimize all these parameters based on your real applications. Okay, so this is some testing for the microcantilever to different low impedance, and this is the voltage output and power output on this axis. And you can see for rectangular, we can generate about 0.5 G at around 100 microwatts. And for triangular one, the same acceleration level, we can reach around 100 or 145. So it's increased about 35.7%. And for the reliability lifetime experiment, we are now proud to say our device is quite reliable. Of course, the other reason later I will say is actually already different substrate material. It's stainless steel instead of silicon substrate. The stereosine in micro fabrication process is more reliable because of better mechanical strength. So for the triangular transducer, you can see the blue trace and red trace is a lower acceleration, 0.3 G and 0.5 G and 0.75 G. It's less longer, and the output is constant compared to mechanical. But for even larger acceleration, for example, here is 1 G, you can see it's a fail drop to very low output within 1 hour. But for rectangular, it's not. And the reason is also quite simple, because the stiffness, overall stiffness for triangular one is smaller. So overall, the mechanical strength is also worse compared with the rectangular one. So again, it has to be designed and optimized based on your real requirement on the application side. Okay, so this is actually what I did last year from the other peer season, and this is the microcantilever we fabricated. It's also in about centimeter square, and you can see no matter the output voltage, output power, normalized power density is much better than the rectangular one or the triangular one. And also for the model, the simplified, very simple model I just mentioned, when you have a basic excitation, you create a deflection on the tip. But this kind of deflection can also be in the other form other than basic excitation. For example, a lot of researchers are now working on plunking, like mechanical plunking, and this is what I just mentioned. In past year, we are working with Miguel on rotational excitation. So we replace the proof mass with a magnet. And for the rotational disc, if we have also magnet along the circular direction, then we can create a mechanical, magnetic plunking. And with this kind of rotational excitation, because of the harmonic of the rotational speeds, you can expect it's more broad operating range. In different rotational speed, you can get quite good output. And also overall voltage output and power output is also quite good compared to basic excitation. And the other very important impression I want to tell you for state-of-the-art smart scale microelectronics in about centimeter square. In the very beginning, when I talked to IC people, the circuit people, they are also say, oh, you are MEMS, so your power output or your voltage output is low. No, I'm actually telling them you are wrong, because piezoelectric transducer in general is high voltage, low current. Even with the micro machine, the micro piezoelectric anyhow, it's not so micro. It's in MEMS area, people say it's mesoscale. In centimeter square, we can still easily generate voltage higher than 30 volts. So for now, I'm working also on integrated circuit design for interfacing circuit with some professors in my university. We actually have no choice to adopt high voltage process from TSMC that can sustain like 60 volt or 120 volts. So in small scale energy harvesting, it's not actually generate low voltage. It still generates high voltage, but the current is actually quite low. This is also the difficulty on design the power converter, especially the rectifier from AC to DC side, because you are facing very high voltage and very low current, and it's in AC form instead of DC form. Okay, so a material perspective, I'm talking about substrate, piezoelectric material, and also the same thing deposition processes. Okay, so this is actually, just mentioned, my second PhD student. He has to solve the problem left by the first PhD student, the reliability issue. And he's quite clever. One day he came to me and said, can we abandon silicon substrate? This is a big question, you know, because all MEMS people are talking about silicon fabrication from the very beginning. And the silicon microfabrication process is mature and a standard protocol. You can easily do that in like a clean room. But if you want to change to the other substrate, you have to have a strong reason. Because, for example, if you want to deposit film or do etching, people in microfabrication area, they will tell you, you have to consider contamination problem. For example, for certain deposition chamber, you can only put certain kind of material into a chamber. So if you want to change the substrate, then you need to consider is this substrate material possible in all your process, including deposition, etching, and also like a lithography, like double-sided liner if you want to do like a bimorph. Okay, so in the end, I say, well, we try. So we try stainless steel is actually, in the end, we found with a lot of advantage. The major advantage is actually better mechanical strength. The major problem we want to solve was left from the first PhD user about the mechanical strength. The red line here, you see, is actually the yielding strength of the stainless steel and breaking strength of the silicon substrate. So this means that when we do optimization in our design acceleration, at that time we design we take like 1G or 1.5G. We already optimize the stress or strength that's already very close to the yielding strength of stainless steel and breaking strength of piezoelectric material and silicon. So this is also why our transducer break from the beginning. Well, so when we do this kind of optimization, then we found this stainless steel material, substrate material, has the other very important characterization. This stainless steel substrate is a metal material. Metal material, you know, from a material perspective, is a ducting material. Ducting material means it has a yielding necking phenomena. And for silicon or PCC ceramic, it's a brittle material. Brittle material is like glass. When you fall it onto the ground, it's break. It crack. And for metal material, it's ducted. So if you have a metal cup that's falling onto the ground, you only see a dent. It won't break, right? So it's very important. That's when we combine a piezoelectric ceramic onto stainless steel substrate. It's like a reinforced concrete. You have a stainless steel, it's not stainless steel. It's steel inside the concrete to sustain the tension force. Okay, So ductile material, you can sustain tension force and compressive force. But for brittle material, you can only sustain compressive force, but not tensile force. So this is why for our reinforced concrete that's used in general buildings, we need to have steel inside the concrete. So the combination of stainless steel and piezoelectric ceramic is also the same. With this combination, we can sustain tensile force instead of silicon plus PZT. So we did a lot of throughout tests. In the end, we proved that no matter power output, voltage output, for fair comparison, stainless steel is much better than silicon. And most importantly, the reliability is much better. So this is a reliability test for devices with blue trace is with stainless steel, and red trace with silicon substrate. So when we test it at 0.25 G, the red trace is fell after 10 minutes. But for stainless steel, it's sustained longer than 1 hour. Actually, it cannot sustain even longer if you extend the test time. Also, if we cycle the saturation level from 0 to 2.5 G, you can see the silicon one must break at about 2.3 G. This is a smaller beam compared to our previous paper. But for stainless steel one, it can sustain over 2.5 G. And most importantly, because of the yielding or necking phenomenon. So the fail pattern of stainless steel is not like a silicon, it's break instantaneously. It's because of the yielding. You have like elongation of the surface electrode till the surface electrode with some micro cracks developed firstly, and in the end, the surface electrode is tilt. So you can see some like you can predict that it's about to fail. The output voltage will be reduced before it's really fail. So you can see after 2.5 G, it's not dropped to 0 immediately like the silicon one. It's reduced power output or voltage output gradually till 0. So this is the other advantage of stainless steel substrate. So for now, you can see there are more and more people talking about stainless steel, and for also some people like some researchers from like China or USA are now using other metal material like copper. Also have similar advantage compared to silicons. Okay, so I think I will give you this slide later on. So for all these references, if you are interested, you can also translate a paper after this tutorial. And well, let's go back to piezoelectric material. We all know we have different kind of piezoelectric material. The major two different kinds of piezoelectric material. The first one is actually polymer, like PDF or PDF2, and the other kind is actually ceramic. And ceramic material like PZT, PNPT, we can also do application to grow single crystal material. The piezoelectric content will be much higher. Of course, we also have natural single crystal material quartz, but that's very expensive and very difficult to fabricate. So in general, piezoelectric transducer fabrication will eliminate the natural piezoelectric material quartz. So in general, the artificial piezoelectric material, the most popular one is actually the polymer one, PVDF, and ceramic PZT. And of course, there are also a lot of research about the lead-free ceramic, like KNN or nitride. But in general, nowadays, piezoelectric performance, the piezoelectric constant are all still much lower than like PZT or PMTC. So this is also why PZT is lead content material, but as in Europe, EU is an exception for the lead-free requirement electronics materials, because for now we cannot find a better alternative. So there's some different comparison for like flexibility. Polymer is definitely better, but the dielectric constant, the piezoelectric property, the single crystal one or ceramic one is definitely much better than polymer one. So for now, we still feel like ceramic one, PZT or PMPT is the best choice for smart scale energy harvester at this moment. And for CMOS compatible process, people will like aluminum nitride or aluminum oxide. But these two general microfabrication or semiconductor process compatible material has much worse piezoelectric property compared with PZT. So this is why for the past 10 years there are a lot of effort on grow thin film or sync film PZT for different piezoelectric, small scale piezoelectric transducers. Okay, so let's continue with some literature. If you are interested, you can later trace by yourself. So again, let's recall the design trade-off. Now, we are talking on a material, figure merit, and also the piezoelectric effective volume, including a lifetime. So here, if you want to maximize the piezoelectric material coupling, we want to have higher figure of merit piezoelectric material. But in general, for example, we can try to grow epitaxial single crystal material, but the processing difficulty is higher, much higher. For example, like quartz is hard material, single crystal. And also, for the past 10 years in European piezo MEMS program, there's also the other process called pulse laser deposition that can grow same film silicon substrate laterally. But again, the post fabrication is still quite difficult because it's tough material to etch. So it's very difficult to fabricate transducers. And if you want to maximize the piezoelectric material effective volume, we can have a thinner beam, thinner substrate. But the thickness of the piezoelectric film is generally limited by the process itself. I will mention this later. For example, like the CSD, the high performance PZT processes based on social process, it can deposit very high performance PZT thin film. But the thickness limited is about 2 to 3 micron. Also, the PLD, I just mentioned, the single crystal PMPT thin film, the thickness is also limited by the process by about 2 micron. And again, the mechanical strength you have to take into consideration. If you have thinner piezoelectric film, is ceramic, brittle material, thinner substrate, either as a silicon or stainless steel, it leads to poor mechanical strength because even silicon has better mechanical strength than piezoelectric ceramic in general. So you will have, again, a design trade-off between these two factors. Okay, so for small scale piezoelectric film deposition, on the top is a different fabrication methods. For example, MBE is epitaxial if you want to grow single crystal material. CSD is the high performance piezoelectric PZT film based on social process. That's texture aligned to the silicon axis of 100 or 110. And POD is a pulse laser deposition, as mentioned. It can grow PMPT single crystal film. And for thin film, around 10 micron, we have two processes in my lab. Screen printing is actually already quite mature. It can grow film around 20 to 50 micron. And also aerosol deposition. This is the dedicated method we adopt in our lab, originally invented by a Japanese researcher about 20 years ago. And the other major method, as you can see, a lot of research is to thinning from a bulk PET material. For bulk PET material, we say the sintering processes are like to sinter a ceramic plate or ceramic cup. It has a thickness limitation. It's very difficult. It's hardly to go below 100 micron. The reason is very simple. When it's too thin, it's become too brittle in a sintering process. If you touch it, it will break. Okay, so the bulk PET ceramic material thickness is limited to about 100 or 120 micron. For thinner ceramic plate, it will break. So a lot of researchers are working on starting from like 100 or even 200 bulk PET material and polish it, thinning it to around 20-30 micron. But it also has certain limitation. I heard from some of my colleagues in the community. You probably will see him in this workshop. That's AE. They are working on the pacemaker energy harvesting. They is working with a company, French company. They can also do this kind of thinning process. And the limitation I heard is around 20 micron, because if the thickness is even thinner, you will have too much imperfection, crack inside the film. So the overall piezoelectric property will degrade very quickly. Okay, so with this method, you still have certain kind of limitation. Okay, so this is actually the figure memory on the blue axis for different material, and this is the piezoelectric constant alone. Here we are talking about aerosol deposition. This is originally invented by a Japanese professor about a Japanese researcher about 20 years ago. We can grow thin thickness around 5 to 20 micron, and it's actually a physical deposition method. You can see from the animation. Here we put the piezoelectric powder, PZ powder, into this bottle, and it's suspended and with high pressure gauge to blow to bring the powder into this backing chamber. Because of pressure difference, the particles will be accelerated, and when it's jetting out from the nozzle, it will hitting the substrate here upside down with very high speeds. So with this kind of deposition method, because hitting the substrate with high speeds, it can deposit a very composite film, and also the impact cause some local heat, so it's also help on the sintering or crystallization. Of course, after this process, you still need to do annealing or heat treatment to get a beta crystal states, and then you also need to do the polling process. Okay, then this process is the other thin film technology. It's using the bulk material sintering, and although in theory you can get figure memory about 48 gigapart as general bulk PET material, but as I just mentioned, when you thinning the film, you will generate the crack inside. The percentage will be higher, so the overall figure memory is actually degraded. If you want to have a very thin film, then possibly it's not possible lower than 20 micron. Okay, so screen printing here, again, theoretically you can get around 48 gigapart to fly. But for a single thing, for screen printing, you have to have the PZT powder that's mixing with certain kind of organic solvent to have it's like a paste or like an ink, so you can print them. And again, when you do heat treatment, all this organic solvent will evaporate and create crack inside the material. You can see some crack. So overall speaking, the piezoelectric property, or we say the figure memory, will degrade a lot compared to aerosol deposition or bulk material. And the thin thickness you can fabricate with this method is around 10 to 30 micron. And then thin film technology. This is the PLD, pulse laser deposition application method I just mentioned from European Piezoelectric MEMS program. You can see here it can reach very high figure of merit, and it is so far as I know the thin film, the best single crystal piezoelectric material with best piezoelectric performance. But the disadvantages, the following process is very difficult because you are facing a lot of very hard material to etch. So I got a partner in Norway, Sintef Research Institute, and we actually had a project working together. But in the end, they actually failed to do the following fabrication as energy harvester because of the following fabrication difficulties. The other thin film technology, this is actually the mainstream piezo MEMS process for now. It's called CSD, chemical solution deposition. It's an improved version of sol-gel process, and it's already quite mature. You can actually buy a machine that's doing this kind of CSD material with complete recipe, and it's also so-called like texture PZT. That's aligned to 100 axis of the silicon substrate, and it can generate the quite high performance piezo like a PVC film. The figure of memory is about 12 gigapascal, and the disadvantage is typically require SOI wafer that's quite expensive. And also the thickness is also limited to about 2 to 3 micron. Okay, so this is a different thin film or thin film fabrication methods we can compare here. For thin film, I define as for smaller than 2 micron. Thin film here is larger than 2 micron, and in general, I hope it could be larger than 10 micron. So the right rectangle here, our focus is at the CSD. If you want to fabricate high performance piezoelectric transducer that's not large, you want to have very good piezoelectric performance and silicon base, then CSD is the best choice. But again, for energy harvesting, the mechanical issue, the reliability issue, silicon-based transducer is not that good. So if you want to do thinner film and alternative substrate like stainless steel or other metals, then you can try like aerosol deposition or screen printing. And the advantage is it can deposit different substrate, and also it can have larger piezoelectric effective volume. And the cost is also lower. For example, like aerosol deposition or screen printing, you do not need to fabricate the process inside a clean room. And it's also our processes as work less deposits in room temperature. But of course, the figure of memory, the piezoelectric performance is worse than CSD, the chemical solution deposition. And again, some literature review for different fabrication process. If you're interested, you can translate. I will give you the link of this slide stand out. And for the state of the art, or I say the current piezoelectric harvester, we fabricate at my lab. The overall process is like this. With starting from 301 stainless steel substrate in around the thickness is around 50 micron or 60 micron. And with this thickness, you do not need to do the backside etch and the back micromachining of typical silicon-based transducer. So this is also one of the reasons the overall fabrication cost is much lower and simpler. And then we deposit PZT on the top and use lithography to define the pattern. And also, we can deposit bottom PCC to do BIMOS devices. And then the top electrode, we use platinum and titanium as the top electrode and bottom electrode. And the other advantage of stainless steel is stainless steel itself is a metal, so it can add it as a ground connection point. And then we remove all the photoresist, and again we cover the other kind of photoresist and do wet etching to release the beam shape. And then anneal at around 650 degrees C, and on the final step, we glue a Prof mask on the tip to lower the tune with resonant frequency. So this is the final devices we fabricated. It's about the size of a paper clip, and our substrate is stainless steel. So we're starting from a rectangular substrate, 10 by 10 centimeter, instead of typical circular silicon wafer. Okay, so this is a BIMOS piezoelectric energy harvester we fabricated in 2016. And at that time, we can generate about 235 microwatt in 1.5 G. And for blindfold devices, you actually have two electrical connecting configuration. One is in parallel, the other is in serials. This is like you have two batteries. You can connect them in parallel to get higher voltage, or you can connect them in serial. So the voltage is the same, but the current is lower. So this means that you can have a longer battery lifetime. So for the two piezoelectric level, it's also the same. You can choose to have parallel connection or serial connection for higher voltage, lower current, or higher current, lower voltage. Okay, so this is the other optimization. We want to optimize the power output at lower acceleration level. So in 2017, we try to do certain optimization so we can achieve around 350 microwatt at 25 G. So again, this does not mean this one is better than the previous one. It's actually on what is the acceleration level you want to optimize. And that's actually depend on your real application scenario. So if you want to optimize for lower acceleration level, overall speaking, you have to have a less stiffer caliber beam, so we can generate larger deformation in lower acceleration level. So it's again about the optimization, different target of optimization. And we also try PMPT, that's supposed to be a better piezoelectric material with higher piezoelectric constant. So you can see with overall the same geometry parameters, we can get a little bit higher power output compared with PZT. And in the beginning, we actually hope PMPT can give us much better result because the piezoelectric constant of PMPT compared with PZT is much higher. That's also our general impression. But the problem is also the dielectric constant is also much higher. So the figure of Mary, we recall that's d squared over epsilon. When you have higher piezoelectric constant, but you also have a higher dielectric constant, the overall figure of Mary is not that good. So in the end, we actually gave up PMPT, although it can give us a little bit better performance. But the fabrication difficulty is higher than PVC. So in the end, we feel like although PVC is not that good, the power output is a little bit lower than PMPT. But overall speaking, is in the fabrication process much easier. And the price to pay for PMPT is now worse, so we abandoned the development of PMPT in the end. Okay, so at the end of this session, I will like to use the normalized power density of small-scale energy harvester we see this, from this plot. The vertical axis is normalized power density. That's power output of microwatt over G square over millimeter to 3. There's a volume and acceleration level G. So it's actually the power output normalized to external excitation and also the overall volume. And the horizontal axis is the resonance frequency. And the dashed line here is actually a high ISO energy line. That means that if you want to have to get the same amount of energy, if the resonance frequency is higher, although the normalized power density is low, but in 1 second we get more cycles, so we get more energy. In the other end, on the same line, that means that energy is the resonance frequency is low, so cycles per second is lower, but the power density is higher, so we get the same amount of energy. And in this plot, in general, we want to attack this spot. This spot means low frequency but high power density. Why? Because for vibration energy harvesting, in general, the source frequency is quite low, especially if you want to attach it on a large structure. And typical micro or MEMS energy harvester in the very beginning, resonance frequency is quite high, above kHz. Actually, you cannot find natural vibration like on a building or even on a table to vibrate in kilohertz. Yes, you can, but the energy level will be quite low. But from the fundamental physics for micro devices, when the size is small, the natural frequency will naturally go high. You have no choice. Unless last year I met a researcher from UK, also working on micro energy harvester, and their device always has a frequency, resonance frequency higher than kHz. So I asked him, what's your application? And he said, oh, F1 racing car. I always have the resonance frequency in kilohertz range, and the acceleration can be higher than 10G. Well, I say I envy you to have this kind of application. But for general vibration energy harvesting, we cannot have this kind of vibration source. So this spot is actually our transducer. We tune to around 100 Hertz, and the power density is also quite high compared to all previous publications. Okay, so this is a conclusion. And also the challenges. I talked about a lot of design trade-off from the mechanical and material perspective. And this field, researchers are working quite hard for the best decade. We can also see a lot of improvements. But from the application area, we are still a little bit far. A lot of problems we need to solve. For example, we are expecting even beta or high performance piezoelectric thin film or thin film, especially like the single crystal thin film PLD process. In the beginning, we have very high expectation on this process. But in the end, we found on the following fabrication is so difficult. And for the aerosol deposition method that's developed in my lab, is already quite mature. But when we talk to the industry, they are talking about, can you have a high throughput and a mass production machine? I say no, because we build a machine by ourselves. So we still need some time and investment to get this kind of mass production type high throughput machine. And the other interesting topic is transfer piezoelectric film to alternate substrate. For example, like plastic. If you want to harvest very low frequency like human motion, this is also the other interesting topic. And on the transducer design, for the past 10 years, we saw a lot of energy harvesting paper from mechanics area as researchers. They are working on like very low frequency energy harvesting, nonlinear, or frequency up conversion, etc. But most this kind of energy harvesting transducer are bulky and in like 3-dimensional. And for microfabrication, typically we are talking about planar structure because we are processing layer by layers. So how to convert all these researches into a planar structure that can be fabricated in small scale is the other big challenge. And also, like implant or multi-axis motion energy harvesting is also interesting topic. And also, to me, packaging design and also the process development of the packaging is also the other important task before we can have the device to be realized in real applications. Okay, this as my this concludes my tutorial today. Thank you for your attention.